Because participants are there, so why should we?
Okay, okay, sir. Just 1 minute.
ସେ ଆରମ୍ଭ କରିବ
So all of you, welcome to our today's second session, and today we'll deliver our coordinator sir, Dr. Chitaranjan Dev, and he is also my direct teacher since my BTech to up to till now. He's also guided me in BTech, MTech, or during my PhD also, and also whatever my day-to-day life is guiding to till now. I will take the class and everything. And Dr. Chitaranjan Dev sir is currently working as an associate professor in the Department of Mechanical Engineering, Bir Surendra Sai University of Technology, Bulla, Odisha. And he has received his Bachelor Engineering in Mechanical Engineering from Utkal University, Odisha, and his Master and PhD he has obtained from NIT Raulkela, Odisha. And he's the professor in teaching and research since 25 years, and he was also a faculty member in the Department of Mechanical Engineering, SIT Dhenkanal, from 1999 to 2016, and he has served in various administrative positions like HOD's warden, then board of management member, and act as also principal for 7 to 8 years. And Dr. Chitaranjan Dev sir has also supervised more than 100 undergraduate students and 20 postgraduate students, and presently guiding 5 PhD and 2 MTech scholars. And Dev sir also far published that 20 articles in the international journals of repute and 25 papers in proceeding of national and international conference. And he has also delivered many talks in conference, seminar, FDP, STTP, workshop. And he is a member of many professional society and reviewer of many journals. And he has been engaged in active research in the field of polymer composite for since last 15 years. And today in our lecture number 10, sir will be delivered on in the field of application of Tagochi and utility by solving of the multi-objective problem when machining in electrochemical machining. It will be very wonderful session. So okay, thank you, sir.
Thank you, Santosh.
Sir.
So, for your brief introduction, and dear participant, no need to again welcome all of you. So, due to bandwidth problem, I can shall I switch off my camera? The presentation is visible?
Yes, sir. Yes, sir.
So I have to
sir,
deliver
please,
this
sir, please
lecture.
change the slide whether we have confirmed, sir, slide. Yes, sir. Yes, sir. It is okay.
Okay. So based on, I am actually working in natural fiber polymer composite since 15 years. But today's scenario and looking into the features of this FDP, recent advances in manufacturing processes. So I want to deliver some recent advancement in this ECM process. Then how you will how the utility-based Taguchi being applied to optimize the process parameter we'll discuss in the session. The content introduction to ECM, hybrid machining, and I want to enlighten some features or spotlight some that basic working principle of. Hello, pardon. Is there any problem?
I think no, sir. Any problem from participants? So we'll continue.
Okay. Then I will briefly discuss about this laser-assisted electrochemical machining, ultrasonic-assisted electrochemical machining. Then we'll go to our main topic that what is utility method and how we are optimizing the process parameter to that optimize the ECM process. So basically the machining referred to the process of cutting a piece of raw material into different shape and size to come up with final product. And during this FDP last whatever session that we have completed, all of you I think cleared about this conventional machining, non-conventional machining. But I like to say about something that machining is considered as one of the most important manufacturing process, whether it is a conventional machining or non-conventional machining. The industrial revolution and the boom of manufacturing sector can be tracked back to the development of various machining operations. Generally in conventional machining usually involves changing of shape of workpiece using a tool made of harder material. Using conventional machining method to machine hard metal and alloys means which is increased because these metals are now in demand and which require more energy and they are require more cost to machine. And in some cases, this conventional machining process may not be feasible to machine all those metals. That's why, like you can say Inconel 718 or titanium, all these exhaustive materials are there which cannot be machined by this conventional machining. That's why we go to the non-conventional machining and ECM is under that category. So why ECM? Because this process we require, because it is very much difficult to machine the hard and exotic material like titanium, aluminides, Inconel, other materials like that, which cannot be machined by a conventional machining process. As ECM is independent of the workpiece hardness, so we can machine all those material by electrochemical machining process. Similarly, cutting small or odd-shaped angles, intricate counters, or cavities that cannot be done by conventional machining. Machining of complex profiles like turbine wheels, turbines, that jet blades, machining cavities in forging die, drilling deeper hole and irregular shape holes. Both external and internal geometries cannot be machined through this conventional machining, so which can be done by this electrochemical machining. Fabrication of thin wall part, that is also another limitation for the conventional machining. Rough corner or edge cannot be turned into a smooth part. That is also another difficulty. Similarly, for mass production, as per industry point of view, mass production can be only made by this unconventional machining. ECM gives a new perspective to this machining process, but it is used in its use is limited to the material those who are only electrically conductive. It is a machining process in which ECM is a machining process in which metal particles are removed by electrochemical process instead of standard machining methods. It is based on the principle of electrolysis in which anodic solution of workpiece occurs. And I want to say more about this electrolysis, how it is happening. Electrolysis is the passing of the current between two electrodes in an electrically conductivity solution called electrolyte, which complete the circuit. Just you can refer this diagram. It is a simple example of electrolyte process in between an impure copper anode and pure copper cathode in a solution of copper sulfate with a constant current source connecting two electrodes. First, these copper atoms from the anodes are dissolved and travel through the electrolyte to the cathode where it subsequently deposited. This process, the deposition of these atoms on the cathode is called electroplating. If we reverse this one, then reverse of this electroplating is nothing but the electrochemical machining. Instead of depositing these atoms, if we flush out, then we can say the cup machining is taken place at the end. Copper ions that move through the solution in several mechanisms. Basically, it depends upon three different mechanisms. The first being called diffusion. Diffusion is the movement of ion within a solution influenced by concentration gradient. Ion moves from the area with higher concentration to lower concentration in an attempt to equalize the concentration throughout the solution. In case of the concentration of the copper ion and the anode surface is much higher than the concentration of the copper ion in the bulk of the solution. Hence, the copper ion diffuse away from the anode towards the bulk solution and the copper cathode. The concentration of the copper ions at the cathode surface is lower than the bulk concentration because copper ions are consumed at the cathode surface. The ions also travel to through the solution in the second basis is called migration. Migration is nothing but the movement of the ion due to the potential field. In the example, you can see the copper ions are electrostatically attract to the negatively charged cathode. Usually, in electrochemical experiment, examining the electrode reaction, a background electrolyte with a higher concentration is used to mitigate the effect of migration in the solution. The majority of the current is carried by background electrolyte, so the effect of migration on the species being studied is negligible. The third mechanism is the convention, in which ion could move through the solution. The convention is the movement due to the external mechanical force such as stirring or bubbling of gases through the solution. In case of copper electrolysis, the solution is unstirred and kept at a constant temperature so the ion not subjected to any large convection effect. Be that natural or forced convection, for example, stirring the solution. We can see the reaction that taken place during electrolysis at cathode and anode that marked here. There are two reactions occur simultaneously. This prevents the charge accumulation anywhere within the circuit. There are also counter ions in the solution, so solution remain uncharged. The impure copper anode is dissolved and hence reduced in mass. The insoluble impurities collected under the anode. No other reaction takes place at either electrodes as copper is less reactive than hydrogen. If we'll consider instead of copper there is other metal, then hydrogen also they are having a reaction taken place, and the hydrogen gas would have been produced at the cathode. So this is the basic concept behind the electrolysis process. In ECM, the removal of material is of similar basis, and it utilizes the anodic solution dissolution process. It actually the ECM utilizes the anodic dissolution process used in copper electrolysis, but confines the current with a different method to allow more precise and accurate dissolution. This enables the different shape and counter to be machined using this method. You can see the brief diagram, it is a schematic diagram of a ECM setup. The tool cathode is positioned close to the workpiece, which is anode, and at low voltage, high amperage direct current is passed between them by an electrolyte flowing through the anode cathode gap. Material is removed by anodic dissolution and is carried out by the electrolyte. A charge exchange takes place between the cathode and the anode in an aqueous electrolyte solution which targets the specific area of the workpiece. This can be used to create counters, ring dots, groups, or bell holes with no contact, but with a high precision. The removal of material is precipitated from the electrolyte solution in the form of metal hydroxide. The entire electrochemical machining equipments that consist of these four systems. One is DC power supply, second one electrolyte circulation system, Third one is control system, and last, the mechanical system. As per industry point of view, the DC power supply that the electrochemical machining is, you know that the machining rate in electrochemical machining is proportional to the electric current density. In order to achieve high value of the machining rate, electrochemical machining is commonly performed at high direct current which exceeding around the range of 1000 amperes. The gap between the tool and the workpiece must be low for high pitch correctness. Thus, you can say the voltage must be small to prevent the short circuit. So, as for industrial ECM machine, the range of voltage is recommended to 5 to 25 volt. The control system use some of this electric power. Electrolyte circulation system, the product of electrochemical reaction should be removed from the gap between the workpiece and the tool. Accumulation of the reaction product causes decrease of process efficiency. The reduction of the rate of and also reduce the rate of machining. Therefore, electrolyte flow speed should be high. Commonly, it is ranges from 300 to 3000 meter per minute. The inlet pressure should be in between 0.15 to 3 megapascal. Then, if we're talking about the control system, the electrical parameter of the process means the voltage and current, tool feed speed, parameter of electrolyte circulation system, that is inlet and outlet pressure of the electrolyte, temperature of the electrolyte. All these things are to be controlled by this control system, which provide a stable and efficient operation of unit. Mechanical system consists of a table or a framework enclosed, means it prevents the electrolyte from spilling, enclose the workhead. The tool are also the part of the mechanical system. One of the most important parameter of the electrochemical machining is maintaining the constant voltage level. This is achieved by the control system providing a movement of the tool at a constant speed equal to the linear rate of machining. The process is steady state, is performed at a constant. Typically, the gap is maintained between 0.1 to 0.4 mm. So this is the main role of this mechanical system, and in mechanical system, frame fixation of the workpiece provided by the fixture, the table and the frame is also important for the stable operation of the system at a constant gap. Now, the advanced material play nowadays an important role in modern manufacturing industries, especially in automobile, aviation, cutting tool, dyes, mechatronics, nuclear, biomedical, computers industry, etc. So, using the conventional machining process for such material may result in excessive machining cost and degradation of some of their useful property. Therefore, manufacturing industry is facing challenges mainly from continuous development of use of DTM material in the various key and strategies of industrial application. So the challenges that to be overcome by the advanced manufacturing process, it can be overcome by using the hybrid machining process. The challenges like drilling an the hole at the wall, drilling large number of closely spaced wall, machining at nano, micro, and meso level, machining of part with typically integrated feature, machining deep hole on a curved surface, like in turbine blades. These are some challenges that faced by the advanced machining process. So it can be only overcome by the hybrid machining. In hybrid machining, you can say uh, the conventional mechanical machining technology are limited by the strength of the tool and the mechanism of the chip removal, which mainly involve plastic deformation. These technologies are not suitable for machining hard to machine material, including highly brittle material. Similarly, non-conventional machining process also have some limitation, especially due to their process physics and material removal mechanism. For example, you can say laser machining is limited to certain aspect ratio. EDM and electrochemical machining are limited to machining of conductive material. Precision of water jet machining is limited to hydraulic jump of the jet. Therefore, in order to satisfy these challenges, machining needs two or more hybrid process can be combined to meet one or more machining objectives. So the aim of this hybrid machining process, where it can shorten the existing process chain by combining two or more process on the same machine platform. It can combine the process capability of different process into one hybrid process. These are the main aim of this hybrid machining process. Hybrid machining process uh, or hybrid production manufacturing means combination of the process or machines in order to produce a part in a more efficient and productive way. The general objective of hybrid manufacturing is that 1 plus 1 equal to 3, meaning that the positive effect of hybrid process is more than the double of the advantage of the single process. A hybrid process can be used in different terms like combination of different active energy, different active energy sources which act at the same time in the processing zone, or all constituent processes are directly involved in metal removal, just like laser electrochemical machine, where both these things are being combinedly responsible for machining. Assisted type process in which only one of the participating process directly remove the material, while other process is only to assist the removal by having positive effect on the condition of the machine. Hybrid machining integrating the different process within one machine platform. To achieve this aim, hybrid machining process will need to follow the least one of the following principle, that within the existing material process window of a process, improving the existing process capability, fulfilling two contrary machining objectives, gaining significant benefit to interaction of different process energy. In addition, being cost effective and not causing hazard and toxic waste as also important design principle for a hybrid machining process. So here you can see the classification of hybrid machining process, or that assisted hybrid machining process. Under this hybrid machining process, laser assisted, vibration assisted, fluid assisted, magnetic field assisted. So several different processes are there to assist the removal, metal removal. But in combined hybrid machining, electrochemical, both the material removal process are being combined effect, and both are responsible for the material removal. Like electrochemical discharge machining, laser electrochemical machining, electrochemical grinding, electric discharge grinding, like that. So, entering to the this hybrid machining, we'll discuss about laser assisted jet electrochemical machining process. The objective of this process is to employing a laser is to improve the precision by better process localization. It is a hybrid process that combines the laser beam with a electrolyte jet, thereby giving a non-contact tool electrode that remove the metal by electrochemical dissolution. This setup is consists of electrolyte supply system, laser delivery system, power supply system, and data acquisition system. The laser beam is introduced in the electrolyte jet through the sapphire window. The low power laser beam, the power is in order of 375, cause the thermal activation of the outer layer of the workpiece. Electrolyte jet cause here the anodic dissolution and leading to faster material removal. Further, the localized heat generated from the laser beam accelerate the electrochemical reaction, thereby achieving a higher metal removal rate. In addition to the localization effect, the laser beam aids in the removal of the surface oxide that form during machining. Thus, it enabling the electrochemical machining of the material faster. The laser heat transmit to the workpiece, and how it works means this laser heat first transmit to the workpiece and enhance the kinetic of the electrochemical reaction, and hence enable the localization of the dissolution to a specific area. As localization of this material removal is important for precision machining because it will not during this general ECM you cannot get a precision machining output. So for a particular point or for machining a micro level, so the electrolyte, the laser being focused at the point. The temperature in the laser localized zone is usually 1.75 to 3.25 times higher than the temperature outside the laser localized area. Due to this increase of temperature, the dissolution taken place at the specific area. The combination specific area and material removal taken place only at that specific points. So this combination of laser beam with electrolyte jet cause higher material removal rate in the axial direction. You can see in this figure the combination of the laser beam with electrolytic jet which cause maximum material removal in the axial direction compared to lateral direction where you can see it is a general ECM electrolyte jet ECM process. So where the material is removed in a wider manner, but precisely when you that focus this laser beam, so at a particular point the heat generation is much more and the dissolution takes place very faster at that point and material being get removed. So for precision machining, this laser assisted electrolyte jet electrochemical machining is preferable. So we can say the combination of the laser beam with electrolyte jet, the material removal being faster and it is being precise to a particular, it can be precise to a particular point. Laser workpiece and laser electrolyte interaction also cause higher material removal rate in the axial direction also. Next, we'll talk about this ultrasonic assisted electrochemical machining process, where the objective is of using this manifold is the ultrasonic vibration facilitate the removal of the reaction byproducts and heat from the machine zone, which favors the diffusion of minimized passivation, create optimal hydrodynamic condition and improves aspect ratio and influence the electrolyte reaction through sonochemical reaction. In ultrasonic vibration have been applied to the tool electrode, workpiece and even electrolyte with the similar objective. You can see the schematic figure of this ultrasonic assisted electrochemical machining. It is a schematic diagram of ultrasonic assisted ECM drilling setup where the tool electrode is subjected to ultrasonic vibration. This setup mainly consists of a direct current, pulse power supply, motion control system electrolyte circulation system, ultrasonic head, which consists of a transducer coupled with the ultrasonic generator, and horns for transmitting the ultrasonic energy to the tool. One of the important phenomena in ultrasonic assisted electrochemical machining is transient cavitation and microbubble generation. The ultrasonic vibration lead to the cavitation microbubbles near the surface of the tool and the workpiece electrode, and the gap condition favor their growth. The collapse of microbubbles in a very short time generate high temperature and pressure, which are favorable for mass and charge diffusion in the machining gap. Thus, the electrolyte flow and electrochemical reaction are benefited. Besides, the process parameter like current density, voltage, pulse parameter, and electrolyte concentration involved in ECM, the amplitude of ultrasonic vibration plays an important role. The low amplitude do not give additional benefit compared to general ECM, but too high amplitude affect the machining, again the too high amplitude affect the machining precision, especially where machining micro-dimensional features. So there exists an optimal amplitude which favors the electrolyte diffusion and removal of byproduct from the machining zone without compromising the machining precision. So the optimal amplitude depends upon several factors like machine condition, method of actuation, and technological specification of transducer, dimension of the features to be machined, required aspect ratio, and so on. If we summarize this hybrid machining process, we can see here the laser assisted electrochemical machining process that involves laser and electrochemical both machining both. The main process parameters are laser average power, laser pulse energy, repetition rate, where ECM parameters are voltage, current density, electrolyte type, concentration of pulse parameter. The advantage, improve reaction kinetics, localized material removal can be done by this laser assisted electrochemical machining. If we talk about the ultrasonic assisted electrochemical machining, ultrasonic vibration and electrochemical process both are being combined. The main process parameters are ultrasonic frequency, amplitude, tool design, and ECM parameters, whatever they are in the previous process. We can see the advantage, it improve the electrolytic diffusion, improve the mass and charge transport, or reduce the precipitation. Now we'll go to enter to our main subject, that is multi-objective optimization of electrochemical machining of aluminum boron carbide composite steel composite by utility method. Here a hybrid metal matrix composite we have taken because it plays a significant role in various fields of aircraft, marine, automobile industry components, and many more. The study is dealing with developing a new composite such as aluminum alloy that LM6 with boron carbide as insert. Here we have taken different percentage of percentage of boron carbide for insert in a aluminum alloy matrix. Because we choose this aluminum LN6 base material because it has excellent resistance to corrosion in atmospheric condition, excellent castability, but it has medium strength and cannot be heat treated. Its strength reduces rapidly in high temperature. Due to its poor elasticity, it is difficult to machine. So, to machine this, we choose ECM. The application of point of view of LM6 aluminum is in generally in marine on deck casting, motor cars, water cooled manifolds, and jackets and road transport fittings. So it has a very vast application in different areas. We choose the boron carbide insert here because it is one of the hardest ceramic material due to its attractive properties, including high strength, high hardness, good chemical conductivity, and neutron absorption from radiation. We choose this boron carbide as a insert. And we have fabricated this composite by star casting process. In star casting process, we put this base material in the furnace and raise the temperature to 800 degrees centigrade. Then we add different amount of boron carbide inserts powder, and stirring for 10 minutes with a speed of 300 to 400 RPM. Then we fabricate this fabricate this composite by feeding this mixture into the mold. Then from that casting, we select the material with dimension that what we have going for machining. The dimension is of 25 diameter and 20 length. Sample we are fabricated with the help of this star casting. And the experiment was conducted in by Metatech ECM setup that we have in our university. The setup consists of a control panel for charging voltage, current feed rate, and etc. A machining chamber is in which tool and workpiece are fixed, a pump for circulating the electrolyte, and tool feed system is there to maintain the constant gap between the tool and the workpiece. So this is the fishbone diagram of the ECM, and the parameters are mentioned. And we are machining the composite, that metal matrix composite, with this machining parameters, and different composites are machined here with because we have fabricated this metal matrix composite with 2.55% and 7.3% 7.5% reinforcement of boron carbides. Now, with how to optimize the machining process, we use the utility method. Now, what is utility? Utility can be utility represent the satisfaction that the customer service customer receives from the choosing and consuming a product, process, or service. Utility can be defined as a usefulness of the product or a process in reference to the level of interaction to the consumer. Hence, it represents the satisfaction that the consumer receives by choosing and consuming a product or service. In other way, the satisfaction provided by all attributes of the product or the process to a decision makers, means the consumer basically, is known as utility of the product or the process. You can see example when you go for purchase a car, the attributes are like the fuel efficiency, ground clearance, safety features, space, AC system, music system, riding comfort. These are the attributes. And different peoples having importance to different, giving their importance to different attributes. Someone like this, someone like the vehicle must give a riding comfort. Someone like giving importance to the safety features. So all these are the different attributes that the it is has to be whenever you go for purchase this car, then you are being the decision makers, and how much emphasis you will give to which attributes. The performance evolution or satisfaction provided by the product depends upon the number of product output characteristics. In ECM, the output characteristics generally we are taking, it must have a higher material removal rate, and we can say surface roughness should be less, and more surface finish should be there. So how to how to optimize the process so that that optimum setting give you a you can say a the give you more MRR and less surface roughness. So therefore, combined measure is necessary measure to overall performance by considering the relative contribution of all attributes. So a composite index represents the overall utility of the product. Uh, the overall usefulness of the utility of the product can be represented by unified index, which is sum of individual utility of the various quality characteristic of the product. So the best choice, you can see the best choice provide best satisfaction, which refers to maximization of the utility. The methodology of utility approach is to satisfaction provided by all attributes of the product or the process to a decision maker. Methodology of utility approach to evaluating the overall utility, it is necessary uh, to transform the value of different quality characteristics into a common index. based on the logarithmic scale. The overall utility of a product can be represented by a unified composite index, and which is the sum of individual utility of various quality characteristics of the product. The best choice provides best satisfaction, which refers to maximization of the utility. The unified composite index is to optimize by this Taguchi method. Why we go for this utility-based Taguchi method? Because this Taguchi method works only for optimize of single response problem. The utility concept is used to convert the multiple response problem to a single response. In the present work, utility-based Taguchi optimization method follows the optimization method developed by the Taguchi. Means by this utility method, we convert all the response to a combined response to a single response. So then we apply the Taguchi to optimize that. This is the flowchart of the optimization process. Same Taguchi method is followed, but for multiple response, we'll go to predict the optimum value of each response. Then preference number is assigned, and assignment of weight to each response. Then we'll calculate the final utility value. Then we'll again go for the optimization process. Let us, we can say this YJ is the measure of the effectiveness, experimental data or response data, jth, for jth attributes or the performance characteristics, and there are k attribute exist which evaluating the outcome. The utility function can be articulate as like this. When we go for calculate the overall utility, we have to add all the individual terms. Determination of utility of an individual characteristic that governed by this equation, where Yj is the worst value can be chosen depending upon the quality characteristic of jth attribute. Then for smaller the best, the prime Yj, that the worst value of the maximum worst value is that which is the maximum value among the performance of the attribute. For larger the best, y prime is the worst value, which is the minimum value among the performance of the attributes. Just you see here how we'll decide for like MRR, the worst value that we got during the experiment that is 0.2 gram per minute, and we assigned a number 9 to that. In surface roughness, because we need better surface finish, so surface roughness should be low, so smaller the best. In that case, higher surface roughness value 6 micrometer we have taken as the worst. Similarly, radius of overcut, that the third response that we have taken here, where it is also not desirable. So the worst value we have taken here, the radius of overcut is 1.5 mm, whatever we have got from the experiment. So, the uh, by this formula, we'll determine the utility of individual characteristic, where this Z is a constant and two attribute numerical values, that 0 and 9, are assigned to just acceptable, the worst and most acceptable, the best value of the performance attribute respectively. So when yj equal to yj prime is the most acceptable, that is the best optimal value, so we take this value as 9. Now we have calculated the z value for different response, that for MRR, surface roughness, and the radius of overcut. Now we assign the weight to each response. Uh, Suppose here three responses are there, that is MRR, surface roughness, and radius of overcut. So here we assigned them equal values, like its values are 1 by 3 as but suppose you, for a product you require, your requirement is the production rate must be high, but you are giving less emphasis to that surface roughness. So you can increase the value of giving weightage value, or increase the weightage value of MRR to, that is, you can give 50% weightage to the MRR, and 25% to the surface roughness, and 20% to 25% to the radius of overcut. But the total weightage should be 1, means 100%. Then just you see from the data what we have done here. So we have three machine parameter and one response parameter. So these are the inputs, and all the inputs are of three different levels. So we have to choose a we have gone for that DOE, design of experiment, to minimize the number of experimentation. So for that, we use the generally use the Taguchi orthogonal array, and this Taguchi orthogonal array that is represented by this LA b to the power c, where A is the Latin square, A is the number of experimental runs of row matrix, B is the number of level of each factor, and C number of variables of the factors. So here present work is focused on the 4 factors with 3 levels. The orthogonal array is LA 3 to the power 4. When we choose that one, so when we refer to the table, then L27 is best fit to this input parameters and level. So we'll conduct 27 experiment as per the DOI, design of experiment, and after experimentation we calculate the MRR surface roughness and a radius of overcut for each sample. Then we that convert the data, we calculate the Taguchi SN ratio because the advantage in choosing this SN ratio is to measure the response variable relative to the nominal or the target value. SN ratio transforms several repetition into one value. Uh, and to validate the prediction of optimum performance, SN ratio transfer into the logarithmic scale that it is linearize any non-linear behavior if present. So due to this advantage of SN ratio, we have calculated the SN ratio values for all the response of MRR, like MRR, surface roughness, and radius of overcut. So to calculate this SN ratio, these are governed by this equation, the Taguchi SN ratio governed by this equation. MRR, because we require more material removal rate, so we take the function, objective function as larger the best, and SN ratio values has been calculated by using this equation. Similarly, for surface roughness, smaller the best. So the Taguchi SN ratio equation is governed by this, and we have calculated the SN ratio value for all the surface roughness that we have measured in that 27 experiment. Similarly, for the radius of overcut. Once we calculate this SN ratio, then we have gone for the ANOVA analysis, and according to that, we have first we try to get the optimal setting for the metal removal rate, and by this ANOVA we calculate the things and rank the uh, different factors. Here the factor B is ranked 1 and factor A is ranked 2 and C as 3 and D as 4. So the optimal settings is A3, B3, C3, D1, which can also can be seen from the main effect plot of the SN ratio. And here the factors are A3, B3, C3, D1, which refer to the value. We can see here because A is stands for the applied voltage. That means at level 3 means at a 20 volt, and feed rate stands for B. When feed rate is 1 mm per minute, and C3 electrolyte concentration is 30 gram per liter, and D1 and the reinforcement, boron carbide reinforcement is 2.5. At this case, we get the maximum MRR. Similar operation we have done for the surface roughness, and we are getting the optimal setting as A2, B3, C3, D1, means at 16 volt with feed rate 1 mm per minute with electrolyte concentration 30%, and boron carbide insert is 2.58%. At that case, the surface roughness is less. When we go for the radius of overcut, we will get the optimal setting at A1, B3, C1, D3. These optimal setting we are getting by Taguchi optimization, for single response. Now, our aim is to get a optimal setting for the combined response, and we have to follow the utility theory, or we are applying this utility method to get that value. So, utility of individual product we are calculating by using this equation, and you can see here whatever that values that we have calculated for, you can see just you see utility value that we have calculated here. So for individual response, by using this formula, we are calculating the utility value for MRR, for surface roughness and radius of overcut. By using this formula, so here we are, for the same settings, we calculate the utility value for the MRR, surface roughness and radius of overcut. Then now we have to convert these three response to a single response by calculating the overall utility. The overall utility is being calculated by using this equation, where we assigned weight percentage to different response. In the present study, we have given equal weight to all the response, so that's why we have taken weightage for the MRR, weightage for the surface roughness, and the weightage for the radius of overcut as 1/3. Then we calculate the overall utility value. By observing this overall utility value, we rank the experimental runs according to the value of overall utility. And we are getting the experiment number 18. Experiment number 18 give the appear as a rank 1. So at it means that when the applied voltage at level 2 and feed rate is at level 3, electrolyte concentration at level 3, and percentage of reinforcement as at level 1, at that time we are getting a optimum utility value. That here we are representing in a graph. So the utility value is highest at the experiment run 18. Then optimal factor levels of the utility value. Again, we are performing the ANOVA, and we are evaluate the rank, and we are getting that the optimal setting, the factor A is rank 4, B as rank 1, and C as rank 2, and D as rank 3. Means the factor B, feed rate, mostly influence the utility value, overall utility values, in compared to the C, then D, and least influencing factor is A, means the applied voltage. Now, looking to this main effect plot, here we can observe the optimal parameter setting that we are getting, that is A2, B3, C3, D2. So that means at applied voltage of 16 volt and feed rate at 10 mm per minute, and electrolyte concentration of 30 gram per liter, and the reinforcement is at reinforcement of boron carbide is at 5%. At that case, we are getting the optimal value, means we are getting better response, better MRR, better highly finished surface, and less radius of overcut. To examine this, we have performed the conformity test, and after conformity test, we are getting a error about that is 8%. So that means the optimal setting is at level A2, B3, C3, D2 is the best parameter level for this multi-response system. So to conclude this utility method, the conclusion is like that the utility-based Taguchi method is found to be more fruitful for evaluating the optimum parameter setting. And this approach is efficient enough to solve the multi-response optimization problem. And test result has validated the parametric setting and determined by the utility-based Taguchi method. And said approach can be recommended for continuous quality improvement and offline quality control for a process product. So this is all about, these are the reference that I have taken, and this is all about my presentation. So any question from audience side?
Is there any particular?
Dr. Selvam, particular reason for selecting the Taguchi method? No, there is not any particular reason, but it is because different optimization techniques are there, ANN is there. So, is there not any particular reason for selecting this Taguchi method? But if we consider the algorithm that behind the Taguchi method, it is quite easy and familiar for the student point of view. Any other question? Should we conclude the session? So in the second half, there will be a talk by Deepak. କୋଉଠି ଅଛି? ଆରେ ଯୋଉ PDF ଏଟା ନୁହଁ. There will be a talk by Professor Dipankar Bose of NIT Kolkata, and he will deliver a talk on crossover process hybrid machining. So all are requested to join the session by 2:45. It will be start sharp at 3 p.m. So have a good day. Let us meet again at 2:45.
Okay, thank you, sir, for the nice presentation. We have learned so many things about the electrochemical machining because sir is basically background on composite because still for the fulfillment of our topic name, sir delivered about the ECM, and we have learned so many things. And thank you for the presentation. And also, I believe all these participants have enjoyed this beautiful session. So today we have completed our first session. So again, we'll meet on 3 p.m. For the last session of the today lecture. Thank you, sir.
Santosh,
Sir.
share that. Have you shared the attendance link?
Yes, sir. Yes, sir. Now I have sent.
Okay.
In 2 minutes back, I have sent.
Okay.